time, convinced that it's mine, with her just to keep.
Hello and welcome to the practice problems video on surface integrals of vector fields. Okay, so in number one, we're going to start simply by calculating the surface integral of the vector field, and I'll give you all of the information that we're going to need. So this, or aka, you could think of it like this, where we're dotting it with the normal vector, which I think this form is a little bit more like explanatory of what we're actually going to be doing in the calculations. So the given vector field is z, 0, y, okay? And our given parameterization is g of u, v equals u squared minus v, u, and then a v squared, okay? And also the last thing we're given is u goes from 0 up to 2, and v goes from a negative 1 up to 4, okay? So this is all of our given information, and we're supposed to find the surface integral over this vector field with the given parameterization. All right, so let's start by finding the tangent vectors. Yeah, that's right. So t sub u is equal to the partial derivatives of each component with respect to u. So in the first one, that would be a 2u. In the second one, that would be 1. And the third component is a 0. Okay? And then our tangent vector with respect to v is going to be the same thing, except for now with respect to v. So that would be a negative 1, a 0, and a 2v. Okay? So these are our tangent vectors. And now we want to find the normal vector. So normal is going to be found by crossing these two tangent vectors. Ooh, my v's are kind of funny. Anyways, okay, so we're going to set up. So we have our I, j, and k. And here we're going to have our 2u, 1, 0, negative 1, 0, 2v. Okay, so something like that. So what we're going to get is an I times 2v minus 0, right? This first x here, minus a j hat times 2u times 2v, 2u times 2v minus a 0. And then finally, plus a k hat, where we have 0 minus a minus 1, so that's a plus 1. So our our normal vector with respect to, of u and v is going to be a 2v and then a negative 4uv and then a positive 1. Okay, so that's our normal vector. And then let's see what our f of g of uv is. So in this case, our x is this thing. This is the first component. Our y is u, and our z is v squared. Okay, so f was z, 0, and then y. So z is now v squared, 0 is still 0, and y is a u. All right? So now we need to take these and dot them with each other, right, for our formula. So I'll continue on the next slide. So essentially what we're going to want is the integral over domain D of u and v, and then we have our vector field with g plugged into it, so we can get our u and v there, and then the normal vector as such, and then du dv. So right now what I'm going to find is this part, so I could just plug it into the integral. So we had our f of, so I'll write f of g of u v dot with the normal. So this is going to equal v squared, right? So we have our v squared, our 0, and u dotted with the normal vector, which we calculated to be 2v, comma, negative 4uv, and then a 1 as the last component. Okay, so we're just going to dot this out so by multiplying the first two components, so this one and this one first. So we get 2v to the third. And then if we add it to the product of the second components, that's just a 0. So that's just a 0. And then we have, for the last components, just a u. So our, I guess our integrand, I'm still not sure if that's the right term, but I guess the thing in the integral, the thing being integrated, is going to be a 2 times v cubed plus a u. All right? So we also have our bounds, right? They gave us u goes from 0 to 2, and v goes from -1 up to 4, okay? So now we can just set up our integral. So we get, I guess I'll just do the u's on the outside, and then we'll do v on the inner integral. So then we have our 2v to the third plus u goes in here, right, in this spot here. And then, in this case, it's dv du as corresponding to the bounds, right? So let's do the inner integral first. And we're just going to solve this double integral. So we have 0 to 2, and then if we integrate with respect to v, we get 2v to the fourth divided by 4. So that's a 1/2 in front here. That's a 1/2, okay? Plus u times v, as v goes from -1 up to 4. And then a du here. All right? So then when we plug that in, let's see what we get. We get 0 to 2, and then this is a 1/2 times 4 to the fourth plus a 4u. And then we're going to do minus 1/2 times -1 to the fourth. And then this is a minus a u. Okay? So something like that. And then if we simplify on the inside, we get 0 to 2. And then this is 4 to the fourth is 16 times 16, which is 256. And divided by 2 is a 128 plus 4u. And that's going to equal -1/2 and then plus a u du. So again, simplifying, we get 0 to 2. And then 128 minus 1/2 is going to be, let's do it over here, 256 over 2. Minus 1/2 is 255 equals 255 over 2. So now we have 255 over 2, and then plus a 5u when we combine those. Okay, so I'll continue this on the next slide. So what we get when we integrate is a 255 over 2 times a u plus a 5u squared divided by 2. As u goes from 0 up to 2. All right? And now we're just going to plug things in. So we get 255 over 2 times 2, and then plus 5 over 2 times 2 squared, and then minus 0, basically. So this turns out to be, these cancel, so we just get 255. And this here, you can cancel with one of them, so that's plus 10. So our final answer for this problem is 265. Okay? All right, now for the next problem. So for number 2, example number 2, we have, we're going to find the following. Again, the same like surface integral over the vector field. So something like that. And these just take a lot of practice, I think, to get good at them. But anyways, so this is what we're solving for, and we are given the following vector field of y, comma, z, comma, x, all right? And we're also given the following surface. The surface is actually a plane in this case. So this is the equation of our plane, all right? And we're given that x goes from 0 to 1, and so does y, all right? So nice bounds here. That's not a 4, that's a y. Sorry about that. So that's a y. So these bounds should kind of give you a hint, because they usually give you bounds for your parameter variables. So that suggests that x and y are our parameter variables. Okay, so in this case, that means that x and y take our u and v place. So that means that x is just going to be x, and y is going to be y, and z is going to be some function of x and y. So let's look at this equation here and manipulate it so that we get z by itself. So in that case, we have to, well, I'll just rewrite it here. 3x minus 4y plus z equals 1. So what we want to do is add the 4y on both sides and subtract the 3x. Okay, so we're going to get z by itself, so then that is equal to, I'll actually write it like this, z of x and y is equal to 1 plus 4y minus 3x. Okay, so this is our function of x and y, which goes in the z part. So this is 1 plus 4y minus 3x. This was like, anyways, in a previous video I termed this as h of x and y. But anyways, so this is our parameterization here, alright? So now we can calculate the tangent vectors. So we get t sub x equals 1, 0, and negative 3, okay? And then our t sub y is going to equal 0, 1, and a 4, right? So let's calculate the normal. So we get tx cross with ty. So that's going to be equal to, we're going to set up our thing here. So we have 1, 0, and negative 3. And then a 0, a 1, and a 4. Alright, so we get I times 0 minus a negative 3. So that's plus a positive 3. Minus j, which is 4 minus 0. And then plus a k, which is then just times 1 minus 0. Okay, so what we get is that this is equal to 3, comma, negative 4, comma, 1. Alright, and also, I mean, I know I took you guys through all of this, but also, so I just did this so you can see the process for when you have some given function of x and y as your z coordinate. But also you could have just looked at this equation here and realized that they're the coefficients of the variables. But anyways, that's like a shortcut that you should not. You can use it with planes, okay, but you shouldn't use it for everything, okay. So that's the important part here, is seeing the process of it, and yeah, so the process. Anyway, so now we have our normal vector, and now we need our f of g of x and y, okay? So f of g of x and y, so that's going to be, in the y spot, we're going to plug in a y, because that's what y corresponds to. So we have a y here, but this is where it gets different. Our z corresponds to this long thing. So we're going to plug in 1 plus 4y minus 3x for the z spot, and our x is simply x. Okay, so now with these, so again, this is our normal vector here. So we're going to take this, and we're going to take the line that I just calculated, and we're going to dot them together in our integral, right? So again, the format here is going to be d, where d is our parameter domain, and then we have f of g of, in this case, x and y, dotted with n of x and y, but there's no x and y, it's just numbers, and then dx dy in some way. So again, the bounds on x and y were 0 and 1, so we're going to write zeros and ones, and then in our integral, we had, this thing was the following. We had y, comma, 1 plus 4y minus 3x, comma, x. And then our normal, which we found was 3, well, sorry, that was a weird 3. 3, negative 4, and 1. And then dx, dy. Okay, so let's dot this out. So we still have our integrals here. And then, so the first product is 3y. And then we get minus a 4 times the second component, which is 1 plus 4y minus 3x, and then plus the third component's product. So something like that, right? And now let's just distribute that in. So we get 0 to 1, 0 to 1, and 3y minus 4 minus 16y plus 12x plus x, and then our dx dy. So this turns out to be 0 to 1 from 0 to 1. And then this is, what, 13x minus 13y minus a 4. And then we have oh, sorry, forgot a dx there, dx dy. Okay? So something like that, and now we're just going to calculate the integral like normal. So I'll continue this on the next slide. I guess I'll rewrite it here. So we have, what we left off with was 13x minus 13y minus a 4, and then dx dy. Okay, so from here we're going to calculate the inner integral, so with respect to x. So that's going to be 0 to 1, and then we have a 13 over 2x squared minus 13y times x minus 4x, as x goes from 0 to 1, and then our dy. And this equals 0 to 1. When you plug in 1, we get 13 over 2 times 1 minus 13y times 1 minus 4. And then because everything has an x in it, when you plug in 0, it's just minus a 0. So something like that, okay? And now we have, I'll just rewrite it in simpler form. So we have 13 over 2 minus 13y minus a 4. And 13 over 2 minus 4, I guess I should have simplified that. But anyways, so this is times dy. And then 0 to 1, 13 over 2 minus 4 is 13 over 2 minus 8 over 2. So that would be 5 over 2 minus 13y. And now we can do single variable calculus, yay. And we're going to integrate here, so we get 5 over 2y minus 13 over 2y squared. And this is as y goes from 0 up to 1. So then we have, when we plug that in, we get 5 over 2 times 1 minus 13 over 2 times 1 squared minus a 0. So that is 5 over 2 minus 13 over 2, which is a negative 8 over 2. And our final answer is a negative 4. Okay? Alright, so that is about it for this practice problems video. And I hope that helped as far as like walking you through how to do the steps of surface integrals of vector fields in particular. And a final note, again, just good luck on your homework and keep working hard.
I don't